Most explanations begin with particles, tiny objects, building blocks, pieces of reality. But there is a problem. If the universe is built from particles, why do some resist acceleration while others do not? Why does an electron have mass? Why does a photon not? And perhaps most strangely, why should mass exist at all? We often imagine mass as a property, something an object simply possesses, like color or shape, a built-in attribute, an intrinsic feature of matter. But modern physics tells a different story. Mass may not belong to particles in the way we intuitively imagine. It may arise from something deeper, something that fills all of space, something we never notice, yet cannot escape. In everyday life, mass feels obvious. A truck is harder to push than a bicycle. A bowling ball resists changes in motion more than a tennis ball. Since childhood, we learn that massive objects are simply heavier and harder to accelerate. The idea seems so natural that we rarely question it. Classical physics did not need to. In Newton's framework, mass was fundamental. Every object possessed a certain amount of inertia. The equations worked. Predictions matched observations. The question of why mass existed remained largely outside the theory. It was treated as an input, not an explanation. Then, physics began digging deeper. Atoms were discovered, then electrons, then nuclei, then protons and neutrons. Eventually, an entire zoo of subatomic particles emerged, and a new question appeared. Not why a car has mass, but why fundamental particles have mass. If electrons are elementary, not made from smaller pieces, where does their mass come from? Why that value? Why not zero? The puzzle became even sharper in the 20th century. Physicists developed quantum field theory, one of the most successful frameworks ever created. In this description, particles are not tiny, solid objects. They are excitations of fields: the electron field, the photon field, the quark fields. Every particle corresponds to an underlying field extending throughout the universe. This picture explained an enormous range of experiments, but it also revealed a problem, a very serious one. The equations describing fundamental interactions suggested that certain particles should be massless, not approximately massless, exactly massless. Yet observations disagreed. The weak nuclear force provided the clearest example. This force governs radioactive decay and plays a central role inside stars. Its carrier particles, the W and Z bosons, were experimentally found to be extremely massive. But the mathematical symmetry of the theory resisted simply inserting mass by hand. Doing so damaged the structure that made the theory work. The equations became inconsistent. Predictive power collapsed. Physicists faced an uncomfortable choice: keep the mathematics, lose reality, or match reality and lose the mathematics. Neither option was acceptable. Somewhere, something fundamental was missing. The solution emerged gradually during the 1960s. Several physicists explored an unusual possibility. Perhaps empty space was not truly empty. Perhaps the vacuum itself possessed structure, not matter, not particles. A field, present everywhere, even in the deepest vacuum, even between galaxies, even where no atoms exist. Imagine standing in what appears to be completely empty space. No planets, no stars, no gas, no dust. Classically, there would be nothing there. But quantum field theory describes a different picture. Fields remain, even when particles are absent. The vacuum is not a blank stage, It is an active physical state. Now imagine one particular field behaving differently from all the others. Instead of vanishing in its lowest energy state, it maintains a non-zero value everywhere. Not in one location, everywhere. The universe would then contain an invisible background field permeating all of reality. Particles moving through space would inevitably interact with it, whether they wanted to or not. And if that interaction altered their behavior, what we call mass might not be fundamental after all. It might be the consequence of existing within a universe that is never truly empty. That possibility changed everything. The field proposed to solve this puzzle is now known as the Higgs Field. Its central idea is surprisingly simple. Space is not empty. It contains a field with a constant background value, everywhere, at all times. The field does not switch on around particles. The particles already exist within it, like fish existing within water, or sound moving through air. The analogy is imperfect, but it captures an important intuition. The Higgs field is not something particles occasionally encounter. It is part of the environment of reality itself. Now comes the crucial point. Different particles interact with this field differently. Some couple strongly to it, others couple weakly, and some do not couple at all. That difference determines their masses. An electron interacts with the Higgs field. As a result, it acquires mass. The top quark interacts far more strongly. Its mass is correspondingly much larger. Photons, however, do not couple to the Higgs field in the same way. They remain massless. This explanation can sound deceptively mechanical, as though particles are physically rubbing against something. That picture should be treated cautiously. It is an analogy, not the physics itself. The actual description is mathematical. Mass emerges through interactions between quantum fields. The Higgs field modifies the equations governing particles. What appears experimentally as mass arises from those interactions. The important fact is this: mass is not simply inserted into the theory, it emerges from the structure of the fields. This preserves the mathematical consistency of the standard model, and it successfully predicts experimental observations. The idea was elegant, but elegance is not evidence. For decades, the Higgs field remained a theoretical proposal, a powerful explanation, yet still unconfirmed. If the field truly existed, it should possess its own quantum excitation. Just as the electromagnetic field has photons, the Higgs field should have a particle, the Higgs boson. Finding that particle became one of the great goals of modern physics. The challenge was immense. The Higgs boson is unstable. It decays almost immediately. Producing it requires enormous energies. Only the most powerful particle accelerators could hope to create it. This effort culminated at the Large Hadron Collider, a machine built beneath the border of First One. Protons were accelerated to extraordinary energies, then collided, again and again and again. Researchers searched through immense quantities of data, looking not for the Higgs boson directly, but for its decay products, the fingerprints it left behind. In 2012, a breakthrough arrived. Scientists announced the discovery of a new particle consistent with the predicted Higgs boson. Subsequent measurements strengthened the conclusion. The Higgs field was no longer merely an elegant hypothesis. Its associated particle had been observed. This was one of the most important discoveries in modern physics, not because a new particle had been added to a list, but because A profound explanation had survived experimental testing. The Standard Model suddenly became more complete. Yet, it is important to separate fact from interpretation. The facts are clear. A Higgs field exists within the Standard Model. Its interactions generate masses for elementary particles. The Higgs boson has been detected. Its measured properties closely match theoretical predictions. These statements are supported by experiment. The interpretation is broader. When people say that the Higgs field gives particles mass, they are compressing a deeper mathematical story. The phrase is useful, but it should not be mistaken for the entire explanation. Mass has multiple sources. Most of the mass of ordinary matter, for example, does not come directly from the Higgs field. A proton is composed of quarks and gluons. The quarks receive mass through the Higgs mechanism. But the majority of the proton's mass arises from the energy contained in the strong interaction binding them together. Energy contributes to mass, as relativity requires. So the Higgs field explains a crucial part of the story, not the whole story. And once we understand that, a deeper question begins to emerge. If mass is not simply a built-in property of matter, what does that imply about reality itself?
The intuitive picture of the universe
Is a collection of objects. Each object possesses properties: mass, charge, position. Reality appears built from things. Physics increasingly points toward a different picture: a universe built from fields. In that framework, particles are not the foundation. Fields are. Particles appear as localized excitations, temporary manifestations, observable patterns. The Higgs field pushes this perspective further. It suggests that one of the most familiar properties in existence, mass, is not fundamentally attached to particles. Instead, it emerges from relationships between fields. This is a subtle shift, but an important one. We usually imagine identity preceding interaction. An object exists first, its properties come with it. The Higgs mechanism suggests something different, at least for mass. Interaction helps define the property. The particle and the field cannot be understood independently. The property emerges through their relationship. This does not mean reality is subjective. It does not depend on observation. The Higgs field is a physical component of established theory. The philosophical implication lies elsewhere. The deeper we investigate, the less reality resembles isolated objects carrying intrinsic characteristics, and the more it resembles an interconnected structure of fields and interactions. Mass feels permanent, fundamental, obvious. Yet beneath that intuition lies a network of quantum relationships. What appears simple is revealed to be contingent, dependent on deeper structure. This theme appears repeatedly throughout modern physics. Space may emerge from deeper principles. Time may emerge from correlations. Particles emerge from fields. Mass emerges from interaction. Again and again, features that seem fundamental become consequences of something deeper. That does not mean the search ends. Far from it. The Higgs field answers important questions, but it also leaves others unresolved. Why does the Higgs field possess its particular value? Why do particles couple to it with the strengths they do? Why is the top quark so massive compared with the electron? The Standard Model describes these numbers. It does not fully explain them. Physics, therefore, stands in an interesting position. The Higgs mechanism explains how particles acquire mass, but not necessarily why the universe chose these particular parameters. The deeper origin remains unknown. And there is another reason the Higgs field matters. Without it, the universe would be radically different. Electrons would be massless. Atoms, as we know them, could not exist. Chemistry would change beyond recognition. Stars, planets, biology, and observers might never emerge. The structure of the visible world depends critically on this hidden field. Everything familiar is shaped by something invisible, something present in every region of space, something discovered not through direct perception, but through mathematical reasoning and experimental verification. That fact alone is remarkable. Human intuition never suggested the existence of a universe-filling Higgs field. Nature revealed it only when we looked deeply enough. And perhaps that is the broader lesson. Reality is not obligated to resemble common sense. The universe does not arrange itself according to human expectations. It follows structures we uncover gradually, sometimes reluctantly, sometimes surprisingly. We began with a simple question: why do particles have mass? The answer led somewhere unexpected, not to a hidden substance inside particles, not to a tiny mechanism buried within matter, but to a field extending throughout the cosmos. A field so pervasive that we never notice it, yet so fundamental that without it, the world would be unrecognizable. Mass is not merely a property, it is a consequence of existing within a universe that possesses a particular structure, and that invites a final reflection. When you lift a stone, push a door, or feel the weight of your own body, you are encountering something that seems immediate and obvious. Yet behind that familiar resistance lies a field filling the cosmos, silent, invisible, everywhere. A reminder that the deepest features of reality are often not the things we see, but the structures that make seeing possible.